Good morning, everyone. It's good to see you here. Well, we said at the beginning that all the finalists deserve a prize. And we are not like governments who say, you deserve it, but we don't give it to you, okay? So there is a top 5 prize for each of the participants in the finals. They do deserve it. And it's a moment, Pavel, Adam, to hand the prizes to all 5 finalists. And we'll start with the order of the presentations. So Raya, you're the first one. Congrats. And just could be a photo. Yeah, thank you. Congratulations. Okay, who was the second one? Richard. Okay, Richard, it's also a top 5 award. Richard, all the best. It includes 1,000 euro, okay? So my father taught me that if they give you a prize, but they don't, money will not follow, it's not a serious prize. So if somebody gives you a prize, but it will be without anything, and you will have to pay for the tickets to fly to get the prize, don't fly there. Okay, so the third one is, take it. Yeah, Zilling. You were the third one. Okay, so, no, show it to Zilling. No, come on, to the camera. No. Do you see it actually? Wait a minute. Oh, no, wait. You should see it. Okay, of course we will send it to you. You don't have to come to Warsaw. So you don't have to come to Warsaw. It will be sent to you. Okay, Matis, you're the first one. Yes. Let's do it this way. And last but not least, Max. Max was flying 17 hours, you know, from Los Angeles just to get the diploma. So. Okay, there was a saying in Rome that this primus inter pares, so the first among the equals. So you are all equal. But you know that we have a statue and we have to give it to someone, okay? We just toss a coin. And okay, Richard, you are the only one who brought a partner with you here. You really deserve this prize, so come on. Vicky, show up, Vicky. Yeah, he brought his partner and he really deserved the prize. Are you ready for your lecture? Or you are so surprised that you forgot what you are going to say? I still have some time for you. No. Yeah, don't go. Yeah, that's how it works.
Well, thank you so much, everyone, for the prize and for being here, and congratulations to all the other finalists. And this has been a really wonderful few days. So I'm very excited to tell you about not my dream, but some of the research that actually goes on in our lab. And it's going to be a pretty funny juxtaposition with our dream, because the dream was all about replacing transition metals. And the fact is, that's still a dream. And we still need transition metals. So I'm going to tell you a little bit about the work that we do perform using transition metals in our lab. And I realize this is a crowd that's not just organic chemists, but many, physical chemists and everyone else. So I'm going to try to keep this at a level think of this as a peek into what my lab does in a way that's sort of a snapshot of a day in the life. So I've titled this talk Altered Cross-Coupling Reactions. I thought where we'd start is not actually about cross-coupling reactions, but about what we do in the lab overall. In the US, when you apply to a graduate school, you don't apply directly to a lab. You just get into the graduate program, and then you select a lab afterwards. And so after we recruit all the students and they compete to get in, now the professors compete to attract the very best students. And the way we do that is we give open house talks about what we do in the lab. And often I like to keep these talks pretty casual, and I like handwritten drawings. So I want to show you actually some of how these ideas developed in terms of handwritten drawings and then how they turned into real chemical reactions afterwards. So our group has three main areas. We work on organic redox catalysis, and you might recognize things like this from the talk yesterday. In addition to what I talked about yesterday, we're just interested in redox in general. How can you put electrons into organics, get them out, and how can you use that not only for chemical reactions to synthesize things, but chemical reactions to do other useful processes like separations. Today I'm going to be talking about transition metal catalysis, and so I'll expand on that in a little bit. And then another area that we work on a lot is energy and environment, and we do that collaboratively with other groups, looking at topics like energy storage and carbon capture, and now moving a little bit into electrocatalysis. Okay, so this idea really started from when I drew a little diagram like this. Cross-coupling reactions are very powerful reactions. Even if you're not an organic chemist, you might have used a cross-coupling reaction. And that's how you know a real organic reaction is very useful. It's when non-organic chemists, non-experts, can just buy the materials and use them themselves. Okay, and the reason cross-coupling is useful is you can take an electrophile and a nucleophile. X is some leaving group, and M is some kind of metal or metalloid. And that MX formally goes away, and then the two green and purple groups get linked together. What I'd like to put forth, is that if you have a certain number of electrophiles and a certain number of nucleophiles, well, every single combination gives you exactly one product. In our group, we call this, one recipe, one cake. And therefore, if you have, to a crude approximation, n electrophiles and n nucleophiles, you have n squared products that you can make. That's the chemical space you can access. And when I started out, I had drawn a diagram a little bit like this. What if we could take those exact two starting materials and actually, by changing the catalyst or reaction conditions, get multiple products out? Why would you want to do that? Even if these products can be made some other way, right now, if you have n electrophiles and n nucleophiles, you're not limited to n squared products. You actually have a third axis to tune, which is the reaction conditions. So for example, you could take two ingredients and now not just make a cake, but you could bake a pie, or you can make something else. And this actually could, for discovery chemistry, for discovering new compounds, be very beneficial. Okay, of course, the question is, what are these red arrows and how do we make that happen? Okay, so when we talk about cross-coupling reactions, generally you have an electrophile pool and a nucleophile pool, and depending on what the type of electrophile or nucleophile is, organic chemists love to name things after themselves, right? So you have all of these named reactions, some Nobel Prize-winning reactions. They actually all fall into the same category. All that's different about them is whether you're using a certain kind of electrophile or a certain kind of nucleophile. If you're using an aryl boron or a boron nucleophile, we call that Suzuki coupling. If you're using a zinc nucleophile, we call that Negishi coupling, etc. So all these classifications, they're all important discoveries, but they all fall under the same general scheme. And what we want to talk about today is ways to take those two materials, and this is just sort of a schematic view. Why just couple these two things directly together and make a bond? We can actually insert third things in the middle. It's not a completely new concept, but I want to talk about how we expand that systematically. The other thing that's very interesting about cross-coupling is the bond is usually made where that M and X used to be. But what if the catalyst could, for example, walk over one position, and you could actually make a bond somewhere else? That's another way you might be able to get subtly different products, but using the same pool of starting materials. So these will be the two topics that I want to cover as examples of our research today. And hopefully you'll understand a little bit, not just about the reactions, but about how we approach designing them and solving the problems that stand in the way of making them happen. Okay, so the two reactions I'd like to give you a more detailed introduction to are Suzuki and Buchwald-Hartwig. Suzuki-Miura coupling is a CC bond-forming reaction. So here's a bunch of drugs. And you can see that when you have arenes that are sort of bonded to each other, that's sort of the signal that you use Suzuki-Miura coupling. And here, this is actually a carbonylative Suzuki-Miura coupling, so this is just previewing a little bit. Instead of bonding the two aryl groups to each other, you can actually insert a carbonyl in the middle. There's also a type of coupling called Buchwald-Hartwig coupling. Buchwald was my PhD advisor, and this discovery actually really changed the way drugs look. It allowed you not to make carbon-carbon bonds, but to make carbon-nitrogen bonds. And therefore, as soon as that technology becomes available over the next few decades, you see more and more drugs with aryl carbon-nitrogen bonds. So when you discover reactions that become generally useful in organic chemistry, it actually shapes what chemical space gets explored, therefore what candidates get found, and therefore what functional molecules look like in the future. Okay, so this is just some background. Practically every small molecule drug you can find may have some application of cross-coupling in its history. Okay, we've seen this diagram yesterday. The three reactions that I wanted to highlight are the three that were discovered in the past half century, and these are all cross-coupling reactions, mainly based on palladium. The Suzuki and the Buchwald-Hartwig are among these. You can see that in 1989, no one was using Suzuki coupling, and certainly no one was using Buchwald-Hartwig. So all the drugs at that point were being discovered using other reactions only. So the way the Suzuki-Miura coupling works is you take an aryl halide, X is something like chlorine, bromine, or iodine, and you couple it with a boronic acid, and you make that CC bond. In Buchwald-Hartwig, you take that same kind of aryl halide and an amine, and you make a diaryl amine. So at the start of this project, we thought, well, if you have Suzuki-Miura starting materials already, if you have this pair of starting materials already, why buy another set of starting materials? Is there some way we could just insert an NH group right in the middle and actually make the amine starting from sort of the diagonal partners? Here's the question we always get asked by reviewers and by everyone else. Okay, why don't I just buy the amine and do this? Okay, if you're an academic lab and the amine is widely available, yes, that's obviously an option. And if I only wanted to make this molecule, that's going to be the best option. However, if you're an industrial operation and you've run 1 million Suzuki reactions before, you have 1,000 of every partner, it's very convenient if you can just repurpose those partners and get a completely second set of products rather than having to go buy or synthesize 1,000 more partners. So the idea of repurposing is sort of the core idea here. We're not developing methods that are the best way to make exactly one thing. We're developing ways to generate diversity without purchasing any new materials. We're using the exact same materials to generate a much, much larger pool of products. Okay. So as motivation, as real-world motivation, let's look at this preclinical candidate, for example. Drug discovery is an extremely long process with very high failure rate. Most drugs take 10 to 15 years from the initial hit to actually reach market. And the rate-limiting step of that, not everyone knows this, the rate-limiting step of that is actually synthesis. You usually have to synthesize between 10,000 and 100,000 small molecule compounds before you find the drug that actually makes it into a human body. Okay? And during that campaign of synthesis, before they came up with this final structure, I just want you to take a look at this carbonyl group here. They actually tried many, many different things there. They tried nothing in the middle. They tried an NH in the middle, an N-methyl, an oxygen. Of course, they tried the carbonyl, and they tried an alcohol in the middle. So this is what you do when you make drugs. You make small modifications, and you see, does it get better or worse? And that helps you inform hypotheses. My point is, how did they do this? Okay, the way they did this is for every single one of these structures, they actually had to buy a new starting material, okay, and couple it together. And our dream within the lab is, could we actually start from the same pair of starting materials and then just develop reagents where you can insert a third component in the middle? And therefore, when a medicinal chemist runs a Suzuki coupling, which they do every day, they could just run a second or third or fourth or fifth reaction right beside it, exact same procedure, hopefully, with just adding one commercial reagent, and they just get a whole second, third, fourth, fifth set of products that they can then test. And hopefully that helps us discover drugs in a more economical fashion. Okay, so I'd like to take you through a very schematic, no one likes to see very, very detailed catalytic cycles, but this is just everything is balls, right? And the point of this is not actually to show you how the reaction is going to work, it's going to show you all the things that can go wrong. Okay, so what we want to do is we want this blue and red ball to couple with this small ball to insert in the middle. Okay, first of all, this small ball, whatever this reagent is, it can't be so reactive that it's just going to directly inhibit the catalyst. And you'll see that's a problem we actually run into very soon. This thing needs to be reactive enough that it can make bonds to both sides, so it has to be a pretty reactive reagent. But it can't be something that it can't react when you don't want it to. It has to react at just the right time in a reaction. And remember, everything is just stirring around in solution in an organic reaction. You can't, I can't, I'm not powerful enough to actually tell the chemical, please wait until we're at this point in the catalytic cycle before you react, right? So there's an element of design that goes into this process. Now, the way Suzuki couplings generally work is this red ball comes as a red ball connected to X, and the palladium, as I talked about oxidative addition, right? It steps right into that bond, cuts it in half, and now it's holding these two things. And what we don't want at that point is for the other reagent to come and attach on there and just do, that's regular Suzuki coupling. So we want A, B, C. We don't want just A and C to couple directly and ignore the middle component. Okay, so that's one thing that could go wrong. What we want is, through some order of events, for this middle component to insert either on the red side or the blue side, and then we want the blue component to come on, and we want exactly one red thing and one blue thing, right? We don't eventually want to end up with A, B, A, or C, B, C, B, C. So my point here, even if you don't follow the exact details, my point is you have A, B, C that you want to make, and the more components you introduce by combinatorics, there's more things that could go wrong. You don't want A, B, 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 C. You don't want A, B, A. You don't want C, B, C. You want exactly one order of stuff to come together. And so when we optimize a reaction, we take the reagents that we put in, we take certain kinds of conditions, and then we can expect, this is the product that we're looking for. We hope we get this. And we can expect some of the other products that we might get. This is just the direct Suzuki coupling product. The reason people use Suzuki coupling is it's such a great reaction. It's very, very general, it's fast, it's tolerant. What's interesting in this project is we're not actually, the challenge isn't optimizing a new reaction so much as it is just shutting down a very, very good reaction. We need to make Suzuki purposely very, very, very bad so that it has a chance to insert that third component. So we started with these catalysts based on Brett-Phos, a very nice series of ligands, and that phosphorus here will just coordinate to palladium and create a very active catalyst. And you can see in this dark blue, that's the amount of the desired product we get. And in this sort of lighter blue, that's the amount of the undesired Suzuki coupling product you get. So 70% is a pretty good place to start. But we don't want all of this other stuff. Now, when you use a ligand that's smaller, so Psi is here, this is cyclohexyl. So basically what I'm showing between entries 1 and 2 is if you go to a ligand that is smaller in size, all you get is direct Suzuki coupling. So that's telling us something, right? So now we have this hypothesis, bigger ligands, maybe they slow down Suzuki, and then you have time to do other stuff. Okay, so if we use exactly the conditions shown here, instead of Brett-Phos, we're using something called T-butyl Brett-Phos. That's just a ligand where we put a really big group there, and now you can see we're getting almost quantitative conversion to the product we want. And I'm not going to go through the entire table, but I want to show you what the entries are so that you get a sense of what are the kinds of things we try. We try different bases. Okay, so they ended up using potassium phosphate 4 equivalents as the optimal conditions. You can imagine the students go into the lab and they try everything. 3 equivalents, 3.5 equivalents, 5 equivalents. Organic chemistry tends to still be a very empirical science. I can't write down on paper why you need 4 equivalents. It's just something you try. And then this reagent here is really what does the magic. It delivers that nitrogen atom. And it's actually amphiphilic. It has a nucleophilic nitrogen and then has this leaving group here. And it ends up acting as equivalent to what we call a nitrene, so an N plus minus a nitrene.
What yields over 100%?
Yields over 100%. Right. So these, when we optimize, the way we assess yield is by gas chromatography, and that has some intrinsic error to it. And what you'll see mostly in the literature is people get a yield over 100, and what they do is, oh, I'm just going to call it 100. And we decided that it's actually very important that we don't do that. Okay. Because you get yields of 107. Obviously, you haven't created matter, right? We've still conserved mass, hopefully. Otherwise, I'd be talking about something else today, right? But I think it's it's important when you do your analysis to report the exact actual number you get, because in the context of things, what we're looking for is the best reaction, and the fact that it's over 100. Yeah, exactly. You have to interpret it in its context. Notice also that, so I was saying this reagent gets inserted into here, and notice that there's a lot of other reagents of this kind of class, where you have an amine group and then some kind of good leaving group. You can imagine we probably tried hundreds of these reagents before we found the exact magic one. And it's not every reagent that has this structure actually works well. This is just sort of more for practitioners. A lot of times these aryl boronic esters are easier to use than boronic acids, and we just wanted to show that they work well in this reaction as well. So when you have a reaction that's 96% yielding, what do you do next? Well, for a real user, they're not going to use my model reaction. No one wants to make this as a drug candidate. They want to use it on real-life molecules. So what you do is you provide a guide for people about what kind of reactions are likely to work well and what kinds are not likely to work well. And you see these substrate scope table. I mean, if you read journals, you see these kinds of crazy tables all the time where people have tons of examples. What I want to emphasize is that the number of examples, right? The nature of examples is not that a larger number is always better. It's the amount of information contained in every example. So I think as a field of organic chemistry, we'd love to trend towards doing fewer examples in papers, but with all of those examples actually showing you something meaningful. So if you want to judge a substrate scope table for yourself, just think about all the functional groups that you learn about in undergrad organic chemistry. And if you don't see them in the table, that's not very helpful. If you see them in the table and the yield is 0, that's actually very helpful because you can actually avoid using this method if you have that functional group in your molecule. So it happened. We were very lucky, and this really had nothing to do with design or anything. We were very lucky that this reaction is one of the best working reactions that I've ever worked on. Pretty much everything we tried worked to some extent. So you can put all kinds of groups on the aromatic rings. You can use, for example, an amino acid-derived coupling partner. I won't go through all of these, but I'll just highlight why we did some of these. Free alcohols and other kinds of potentially sensitive groups, cyclopropanes, ketones, nitrogen heterocycles. All of these examples are designed to show you something that a real practitioner may have in their molecule. And if they see this table, they might be more likely to use it. So these kinds of heterocycles that are aromatic and have nitrogens in them, they're all over drugs. So if someone says to you there's a method that's designed to be used for pharmaceutical discovery and there's no examples in the table where it actually works on nitrogen heterocycles, that's generally not a promising thing. And the reason nitrogen heterocycles, I emphasize them a lot in this table, is because nitrogens have lone pairs. And lone pairs can coordinate to metals. And a lot of times if you put nitrogen or sulfur, right, if you put sulfur into these kinds of systems, they can poison your catalysts, and you don't want your substrates to be poisons. Okay, and this is an example where the boronic acid didn't work, and we have to use the boronic ester, and there's also the possibility of using things like tosylates. So these are all with aryl triflates. You can use bromides or chlorides, and we have a bunch of other examples. These aryl chloride examples, the red half, we actually just took commercial pharmaceuticals and just coupled things onto there. So you can see in general the yields are moderate to good, and this reaction is fairly reliable. Okay, so here's a real-life example of how someone might use it. This is a molecule that's actually fairly recently approved, and we looked in the literature, and it's actually made by Suzuki Coupling. So we just ourselves made the two partners. We bought this partner, actually, and then just ran our reaction. And in a totally unoptimized reaction, just using the standard conditions, we got 33% of this amine inserted product. So this is, you can kind of think of this as there's this trend of, single atom editing or whatever, right? You can think of this as, we just sort of cut that bond and insert a nitrogen. This is at least from an ideation point of view, a good way of thinking about how you use these reactions. Here's another example. Here's a coupling that has a chloride and a bromide on there. The palladium can select for the bromide, and it can also have that kind of selectivity when you insert the reagent. In this example, we found that if you actually bought the corresponding aniline, this reagent with the NH2 here, and do the coupling under the same conditions, it actually doesn't work as well. So there are real cases where you can't just buy the other components and couple them together. Plus, it could be that the other amine is unstable or something like that. So, we wanted to show some real-life examples. And what's been really nice is after we published this paper, I had people emailing me saying, hey, I work at blah, blah, blah company, and I ran your reaction, and it made a nice thing for me. And, when your chemistry gets used in the real world, it does sort of validate what you were trying to do to begin with. Okay, so I like mechanism. I'm actually not someone who's obsessed with the endpoint of the arrow, but actually more about learning the rules of chemistry. Obviously, there's a lot of mechanism in here, so I'm not going to go through the mechanism of the entire reaction. I want to go through a couple questions that are very natural when you move to these 3 component couplings. One question is, which component undergoes the CN bond formation first? Is it AB first, or is it BC first? And actually, what's more important than that is how does someone go about figuring that out? How do you actually figure out what order stuff happens in? Is palladium actually involved in both of those steps? That's a very important question as well. And then, of course, what's the order of events? Okay, so I'd like to present to you 2 mechanisms, and I'm going to tell you the evidence in favor of either mechanism, and then I'll tell you my conclusion, of course. First, palladium can undergo oxidative addition. And then this amine, remember we said nitrogens are nucleophilic, so this lone pair can coordinate to the palladium, kick off that X, and you get a species like this. Organic chemists love arrow pushing, right? So this arrow group can actually migrate onto the nitrogen, kicking out this leaving group. So that's sort of an unusual step. And now this leaving group ends up on palladium. So these 2 things are isomers of each other, and all that's happened is the stuff is migrated. Okay. Now, once you've formed the first CN bond between the red aryl and the nitrogen, now you're ready for the second aryl to come in by the boronic acid. That's a process called transmetallation. It's called that because boron's a metal and palladium's a metal, and the groups are just switching metals. And now once you get to an intermediate like this, whenever you see it looks exactly like my product, but palladium's just sitting inside, then what you need to do is reductive elimination. Okay, so this is one mechanism, and we call this electrophile first because this red aryl group comes from the electrophilic side. It's an aryl halide, and in this case, the electrophile is the one that makes the bond to nitrogen first, so that's why we call it electrophile first. Okay, so what we can do if we want to show, at least suggest, is the electrophile first mechanism plausible, is we can just leave out the nucleophile. So if you want to see if A and B can form a bond, it's very simple. You can just leave out C. It doesn't prove the mechanism. In fact, you can never prove a mechanism. But you can at least suggest if it's kinetically viable to do something like that. So we can make, okay, after oxidative addition, we can actually make this intermediate and isolate it, and then subject that to our aminating reagent. And you see, in fact, it does make a small amount of that CN bond. And then what's this? This is actually this thing re-entering the cycle and then coupling with another one of these. So even though the yield of this is low, the combined yields of these gives you some confidence that that CN bond forming reaction can occur. Okay, of course, if there's an electrophile first mechanism, there's also a nucleophile first mechanism. We still do oxidative addition with the electrophile, but what's different about the nucleophile first mechanism is we actually form a complex like this. This is a ternary complex. We have that palladium, we have our reagent, and then we have the aryl boronic acid here. And the aryl boronic acid is the nucleophile, so when we say nucleophile first, we mean that nucleophilic aromatic ring is the one that actually migrates onto the nitrogen first. We get to the exact same intermediate, and then, of course, we all know reductive elimination is what happens next. So can the nucleophile first mechanism also occur? Okay, so to test this one, there's actually a little bit more complicated of a scheme. What we do is we run this reaction, and we look at the total amount of bond formation between this nitrogen and the nucleophile side. Okay, and the reason I say total amount is once you've formed this CN bond, it doesn't just stop here, but it can re-enter the reaction. So what we're looking at is, all the products that have this CN bond already formed. In other words, the sum of these 2 things. Okay, and as we add more and more palladium, you can see that more and more CN bond is formed on this side. Now, there's something I'd like to point out, which is that even in the absence of palladium, these 2 things can actually react in some cases to form some of this CN bond. But as you add more and more palladium, actually the extent of that CN bond formation increases, and that's a very important thing. So in other words, what I'm saying is you can actually form a binary complex without the palladium there, and that aryl group can start to migrate. And if you do that, that can now enter the cycle in a different way, and then intercept your oxidative addition intermediate. You can see this mechanism is getting complicated very, very quickly. Okay, so what our conclusion was at the end of the day is actually this reaction proceeds by multiple mechanisms at the same time. And you might think, wow, that's a very dirty answer. Like, it would be much cleaner if we could just say it's A or B, but science sometimes doesn't work like that. And we were actually, thinking about this from a very optimistic point of view. If you want to take this reaction and build new reactions off of it, if it proceeds by multiple pathways, you actually can connect any of those pathways to a new step or to a new reagent, or if you modify the NH reagent to a different reagent, maybe only one of those pathways can operate. So we thought mechanistic flexibility is actually in general, a good thing for designing new reactions. And basically what we're trying to do now as we extend the reaction is to strengthen that argument with some concrete examples. Okay, so here's some work that we've done on this reaction more recently. For example, if you add a source of carbonyl, a source of CO, you can actually do a 4-component coupling. You can take this thing, add a carbonyl, and then add a nitrogen, and then add this thing. So you get ABCD coupling exactly in this order. And we've actually figured out a way to get A, C, B, D, like flip the middle 2 components, get the reverse amide. That tends to be very useful for medicinal chemistry as well. So you can see the more components you have, the more creativity you can put into exactly what kind of products you're getting. Another thing we can do is we can change the left side component from an aryl to an allyl. So allyls are electrophiles where the leaving group isn't bonded to a double bond, but it's actually 1 over. And you can get these kinds of products out the end. Whether you start with this allyl or this allyl, you actually get the same product, and that's just a mechanistic. That's not something we discovered. What we discovered is just that the nitrogen can insert into these processes as well. So what I'm trying to show here is this nitrogen insertion reagent is actually very general. Okay, we can also use alkyl boronic acids. This has its own set of challenges. And this is an example where we believe it only goes through the nucleophile first mechanism. And we have other evidence of that, but for sake of time, don't want to go through a second mechanistic study. Just want to show you that indeed, the mechanistic flexibility does allow us to extend these reactions in a fairly easy way. You might imagine some of the other reactions we're targeting. Can you insert an aryl or an alkyl or all kinds of other things? That's what organic chemists love to play with. Okay, so in the last maybe 10 minutes or so, I do want to tell us a little bit about the migratory cross-coupling, which was just accepted for publication last night. So hopefully you'll be seeing it soon. Okay, it all started with this, which is a palladium fluorination reaction. I just want you to look here for a second. This is not my work. This is work of my PhD advisor, where they were trying to add F- fluorine into molecules. Yeah, okay, obviously there's all kinds of problems with fluorinated molecules in general in society, but fluorines are also extremely useful in medicinal chemistry, right? In drugs, fluorines can help you prevent things from oxidizing in the body, or you can block labile sites with fluorine. It's like an analog of hydrogen that's a lot more inert. Okay, so they were trying to do fluorination reactions, and indeed it works. And then in some rare cases, they were observing some of this alternative isomer, and this was a really intriguing result because at the time it wasn't clear how you would ever generate something like that. And here was the proposal. Okay, so you enter some kind of oxidative addition intermediate like this, and instead of the fluorine coming to replace the X, that's what normally happens, you actually take this neighboring hydrogen. We were talking about beta elimination yesterday. Take this neighboring hydrogen and this X, and you just eliminate it. And if you eliminate it, you get to something like this. Now, this is, some of you have probably seen benzene before, but when I first saw this structure, it's a very strange thing. It's benzene, but it's benzyne because there's a triple bond in it. That triple bond, most triple bonds are linear, right? So that triple bond is a very reactive one that's bent, and isolating free benzyne is not something you could do. But bound to a metal is something that people have actually looked at quite a lot recently. Now, we eliminated that HX, that H, in this case, X is fluoride. We eliminated HF. You can actually add that HF back on, but depending on which side you add it back on, you can actually, so imagine the HF adds from the top side, so now the H ends up here and the palladium ends up on the bottom. Well, if we flip that over, you actually end up with a different isomer of palladium fluoride. So my point is, after you eliminate HF, it can come back the original way or come back the other way, and what's the net effect of that is the palladium has walked one position over. Now, a tremendous amount of work, okay, some very high-profile papers were spent on designing ligands that got rid of this problem. And when I started my career, we revisited this paper, and we immediately said to ourselves, this is not a problem, this is an opportunity. Because if you could actually do that on purpose, okay, make that reversible, and not do CF coupling, but couple it to other kinds of things, you actually have a manifold for getting a second set of cross-coupling products out of stuff. Okay, so here's the key observation we made. This took us about a year to get to this very simple-looking reaction, where you take an aryl chloride, a para-substituted aryl chloride, and under a certain set of conditions, okay, at 120 degrees in alcohol solvents, which is rather unconventional, that chloride can actually start walking around the ring. You can imagine if it can walk this way, it can also walk that way, so I should have drawn an equilibrium arrow here. And depending on the substituent, depending on what R group that is, the final ratio of meta to para, the final ratio of isomers is dependent on the electronics there. And we can actually start from either isomer and show that they converge on the same equilibrium. That's how you know you're at equilibrium in the first place. So this is good news and bad news. What's the bad news? The good news is we discovered a new reaction. The bad news is that these ratios are not very high. Organic chemists generally don't want product ratios of 2 to 1 or something, because then you have to run chromatography, you have to separate very similar molecules. It's a pain. So if this is an equilibrium process, how could this ever possibly have higher selectivity? You can't use a catalyst to change an equilibrium constant, can you? But here's what we were thinking. Okay, imagine you have an equilibrium between 2 isomers of a palladium intermediate. What you could actually do in a normal case is you could take these 2 equilibrating intermediates and have selective coupling, have one of these react faster towards whatever cross-coupling reaction you're trying to do. And this scheme I've drawn is actually an unsuccessful one, because you can see the barrier for the equilibrium is too high, okay, compared to the irreversible steps, and therefore the selectivity will actually just be dominated by which well it's sitting in initially. What we need to do is to start making the barrier for the irreversible step higher and higher, and once you get to this scenario in the back where the equilibrium is fast and these cross-coupling reactions are slow, you can actually get higher selectivities than what your equilibrium is. This is something called the Curtin-Hammett principle. What controls the product distribution that you ultimately get is now these 2 highest barriers. In other words, the cross-coupling step, is it selective for this isomer or is it selective for this other isomer? The rate at which you deplete these 2 isomers is what governs the final product distribution, not actually their equilibrium populations. So this is just the use of some very, very simple physical chemistry in the discovery of an organic reaction. So does that work in practice? What we do to make those barriers really, really high is we take the nucleophile that we want and we just add it extremely slowly. And I wish I had a slide here to show you this, but we had about a year of failed experiments. Nothing was migrating. Everything was just coupling immediately. And then one day, my postdoc added it over 20 hours, right, took a really, really long nap, comes in and says, it's all the other isomer. That was a really, really nice day, right? You look in the NMR, you're like, oh, it's very clean, but it wasn't what I was getting yesterday. It's a totally new thing that I'm getting today. And so you can see how you can actually now get very high selectivity for what I'm calling the mutant isomer, right? The chloride started on the blue position, and all these couplings are now happening at the red position. And we can do carbon-oxygen and carbon-nitrogen coupling, and I won't belabor the scope there. So I'm not going to show the full experimental mechanistic study, but I just want to draw out the scheme one more time because this is a fairly unusual process. We get to an intermediate like this. So all this spinach on this left side here is all going to stay the same. That's just the supporting ligand. It's fancy looking, but it actually doesn't change that much. What I want you to look at is on the right side. There's an arene and a fluoride. And that fluoride is essential because it can pull off this adjacent hydrogen through a transition state like this. And this, I want you to appreciate, this is a very unusual process. This is not something that is, you get taught in first semester organometallic chemistry. The fluoride's pulling off the hydrogen as the palladium's making a bond to this new carbon, and it's sort of this 5-membered butterfly-like transition state. And you get to this palladium benzyne, and something subtle we didn't appreciate at the beginning is that benzyne can actually go back quite quickly. So you need to give it enough time for that benzyne to actually flip over. And once it's flipped over, the HF can come back. And then you get to this isomeric intermediate. It's exactly what you started with. It looks like the methoxy group has walked 1 position over, but actually what's happened is the palladium's walked one position over. And we found that extremely bulky ligands are needed on the phosphorus. Actually, tert-butyl is not big enough, but we need something called adamantyl. And what that does is it actually makes the ground state look a little bit more like the transition state by just pinching everything together. And I wish I had a picture of that to show you. We'll include it next time. Okay, I just want to show you 2 applications. This is actually not a drug, but an agrochemical. And we took this fragment and coupled it to phenol. Now, normally you use it to make this, this molecule, and using our conditions, you can actually use it to make the migrated molecule. Now, if you do make the proper molecule, you can actually use bromination. This is just an undergrad reaction, electrophilic aromatic bromination. That's selective for the para position. And now you can see why our method is so useful. It's not easy to install a bromine at the meta position, but you can install one at the para position and then just use the migratory coupling to now put the next coupling at the meta position. And likewise, we did the same with sort of this drug. Okay, so in conclusion, 2 reactions that I've shown you today, 2 reaction classes, are cross-coupling that involve the addition of a 3rd component, specifically an amine group, and also cross-coupling that involves bond formation not at the classical position, but actually one position over. You can imagine we're developing ways where the metal might walk more positions or hop from one ring to another or hop and walk, etc. And our dream would be that you could take one isomer of starting material and actually get all the isomers of products out the end. Hopefully that would be quite enabling for discovery. Of course, I want to thank my group. I'm about 2.5 years in here, and we've had the chance to work with some really great people. Highlighted in italics are those who have actually worked on some of the reactions I described for you. I want to especially point out, well, I guess I forgot the name of the person. His name is Paul Onish, and he actually did most of this work on the emanative coupling, and Dr. Yoshia did most of the work on the migratory coupling. Sorry, Paul. And I want to thank all of our funding sources and all of you for your interest in this presentation. I hope I was able to actually convey some of our excitement about these organic reactions and what we think they could do in the future. And I look forward to developing them more. I look forward today to answering any questions that you might have. So thank you all, and thanks again for this wonderful prize. This has been a pleasure.
Questions, comments?
Thank you for your nice talk. So I have a couple of questions. So could you expand your methodology for introducing other heteroatoms, like using, for example, sulfur or oxygen nucleophiles?
Mm-hmm. Yeah, yes, we are definitely looking into that. Oxygen would be very useful. Sulfur, there's been some work done with copper on those, but they're not generally great yet. Another set of stuff that we're looking, so the answer to your question is yes, we'd love to insert other one-atom components. Carbene equivalents are also things that...
Do you have any idea how to do this?
We have many ideas of how to do these and are actively trying. The question is what would be the most useful ones to do, and that's where talking to our industrial partners is something that's really useful. People who actually practice these reactions day to day can actually tell us, I wish your reaction could do this or could do that. In general, it's all about designing that middle component so that it's reactive enough to go in once, but one funny thing you'll find is some middle components, if you make them too reactive, they'll actually go in over and over and over again, and we obviously don't want that. We want to, general in drug discovery, you want to make small modifications, not introduce like a ginormous group in the mid. That usually doesn't help you in terms of information or in terms of designing a drug. So yeah, it's a great question, and it's exactly what we're looking at in that area.
So you obtain secondary amines. So do you observe the formation of tertiary amine during this reaction or not?
We don't observe that because the ligand is just too big. So what he's asking about is those amine products. Is it possible for a third aryl group to come onto there? It's pretty well known that there are certain classes of ligands where that's facile, and if the ligands are big enough, that tends to not be so easy, especially for triaryl amines. If we wanted to do that, we certainly could do it in a one-pot process, but at least for now, we haven't been trying to do that. What we have been trying to do is insert things other than NH. So if you wanted to make a tertiary amine by inserting N-alkyl or N-aryl or things like that, of course, we're looking at reagents that can do that.
Regarding the second part of your presentation, so could you proceed further with migration, like from para to ortho position? Or it's only possible to meta position?
Yeah, I might have deleted the supplemental slides. It actually is possible, but the ortho position is thermodynamically disfavored due to the steric bulk. The reason we know it goes there, two reasons. First, if we add deuterated alcohol solvent, we can see deuterium go into the ortho position. The other thing we could do is we could start from the ortho isomer and see if it goes away because it's an equilibrium process. Forward and backwards are equivalent. And it does, in fact, migrate from the ortho. It's much, much slower. To make those processes happen, I showed you, you have to use very bulky ligands like adamantyl phosphines. The ortho substituent just starts to bump into those. Now, of course, when you have the ortho substituent, maybe the ligand itself can be smaller and there's design there. And we're actually working with, this is actually a very nice system for generative AI models. There was a question about that yesterday. It's a very nice system for that because it's a unimolecular process. That's the key process. There's not two things coming together, but it's just a rearrangement. So what we'd like to do is for the model to suggest to us new ligands that could do that ortho problem, could solve that ortho problem for us. The synthesis of some of these ligands is laborious. I mean, it's not very laborious. My postdocs have made over 100 of them, but it takes time. And you know, we don't know if we're going to need to find 1,000 or 10,000 or whatever to find that magic ligand. If AI can play a role in that, I think this would be a great demonstration.
Thank you.
Okay, thank you very much.
Oh, it's me.
Hello.
Great talk. Thank you. Well, my question is a bit outside of your main topic, which is I would like to know your opinion about possible use of molecularly imprinted polymers for selective organic synthesis.
Mm-hmm.
Have you considered that?
It's not something I've considered. I mean, did you have a specific way of using them in mind?
Well, to get control over the reaction route, the products that you desire,
Mm-hmm.
you need to control, as you mentioned during your talk, on the structure of the transition complex.
Right,
okay?
right.
So that is what in molecular imprinted polymers they serve for.
Yeah, yeah. No, I think that's a great idea. Not in this particular application, but there are applications where we've shown that, for example, there are these photoredox polymers, and actually embedding them into porous organic polymers can actually improve their efficiency a lot. Okay.
The idea is a bit different. Well, if you want a desired product, so such
Okay.
a product is characterized by a transition complex of a specific structure. Okay.
That's true, yes.
So once you control this structure,
Mm-hmm.
you almost can be convinced that you would receive the product that you want, correct? So if you are to synthesize
Okay.
a mimic of transition complex
Right,
and insert it into the molecular imprinted polymer,
right.
then you are a winner. You can get what you want.
I'm not sure you are. I mean, there has been, a program, as you surely know, of these catalytic antibodies that are developed to bind transition
I am
states. and
talking about plastic antibodies, about artificial antibodies, which are molecular imprinted polymers.
But is there a reason to believe they would be more successful than the catalytic antibody effort that, in my opinion, was...
Much cheaper. They are much cheaper than natural antibodies.
Oh, yeah, sure, but a reason to believe scientifically that they should be more successpolymer than what I would say is a partially successful
Well,
program at best.
in literature brings examples of successful application of such polymers. So therefore, I'm asking you if you consider possibility of using them.
I think when we're tackling the very hardest synthetic problems, we should be open to all kinds of methods, and we should be agnostic as to exactly what kind of method we use to approach them. I think in this case, there are challenges besides the shape recognition of the transition state. But to the extent that the shape recognition is important, yes, using polymers in the way you suggested is a promising avenue, yes.
Other questions?
Pavel has a question.
Hey, I actually don't have a question. I have a comment concerning your pedagogic abilities. So leaving aside the great science you presented. So I just want to say this loud. So I'm a trained physicist, and I've been working in the Institute of Organic Chemistry and Biochemistry for 20 years. So I got used to my organic chemistry colleagues, and I got used to what they're working on.
Okay.
But you added to my understanding more than my colleagues did in 20 years in these 2 lectures I heard from you. So I really, appreciate that.
I appreciate that. Yeah, usually when people start with this is more of a comment than a question, it's I close my eyes and just, but that was a very kind thing for you to say, so thank you.
Don't you think that it's a kind of a paradox that Pavel is a trained physicist, I am a trained physicist, and we run the Dream Chemistry Award? And
Well, let me comment. I mean, there is a little bit of a selfish aspect. We actually want to understand chemistry. That's why we invite the bright people to explain it to us.
yeah, this is the best way to understand something, just enter it. I have a question.
Please.
It's quite general. It's a comment and a question, okay? When you show all these organic reactions that for small molecules, okay? Time scale for the molecule is picosecond, femtosecond, maybe nanosecond. And then organic chemists are showing that the reactions run around 20 hours. So it's picosecond and 20 hours. If I scale it up to this macroscopic scale, so say 1 year, okay, this is our time frame. It would mean that if I wanted to react with someone, it would take me the age of the universe, like making a marriage or something like that. So You see,
I see.
I perceive it as a kind of a really strange thing.
Mm-hmm.
Of course, you may say big barriers,
I
but
might-
is it enough? I mean, is it something in it? You know, that you go from the scales of a picosecond or femtosecond,
Mhm.
and your reaction for small molecules run for 20 hours
Right.
before completion.
Well, if you think about that, may be the lifetime of an encounter complex between two reagents, or something like that. But most of those are unsuccessful encounters. So the molecules have to bump into each other, trillions of times or something. For humans, I generally think if you run into someone twice, you know whether you want to encounter them or not. So I think. So yeah, that's it.
For me, it's like that the molecules don't want to react. If they want to react, it would be just immediate, right?
That's one way of thinking about it, but you might be happy that they aren't so. I mean, we want the molecules to exist on the timescales that we exist, at least for the molecules that are functional. So it is important.
Okay. Other questions or comments? Okay, guys. So let's thank all the finalists, all the winners. They deserve it. So. And we have 1 hour break. Very long break. Students usually love it, when they say, wow, we have 1 hour break. Okay, so we have 1 hour break, and at 11:30, I will tell you about my dream. So you are all invited, especially my group. Guys, be here, at least you will be here in the audience.